And so that said, we can start the first IQIM seminar of 2020-2021. Today we have Junyu Liu, who is going to talk about quantum computation and cyberpunkian quantum field theory. It sounds like a very exciting title. So please, Junyu, it's all yours.
Okay, so yeah, can you hear me?
Yes.
Okay, great. My name's let me firstly introduce myself. So my name is Junyu Liu. I'm a 5th year grad student at Caltech. I'm studying theoretical physics, and especially the intersection between the high energy theory and the quantum information. So I'm working in 3 groups. So it's not very usual, but it is a great honor for me to work with 3 theoretical physicists here at Caltech. We have Cliff Cheung and David Simmons-Duffin, who are working on, I'm working on high energy theory with him, and I'm working on quantum information theory with John Preskill, which is who is in the middle here. And this is a brief introduction of my background. So today I will talk about the title is called Quantum Computation and Cyberpunkian Quantum Field Theory. So, but before, so I guess that in the so you might get confused what is cyberpunkian quantum field theory. So this definition is made by this term is made by me. So I will explain later what it means. I mean, so but before the talk starts. Hopefully that this figure here could give you a feeling on what's the theme of the talk today look like. So this is a comic-like figure and made by an artist. So this is basically a description of our teamwork on our work on quantum simulation for some quantum field theory phenomenon, some high energy physics phenomenon. And you could say that there is a spacecraft, and in the spacecraft there are people here and who seems doing they seem to do some research, and they are doing some research, and outside the spacecraft, and there are some bubbles and inside the universe, and this is some bubble, and we call it a cosmic bubble. And then here those people are doing some calculations and that are related to the cosmic bubble, or simulations that are related to cosmic bubble that might be in some sense a simulation of the universe. So these figure and made in this those figures made in this plot is from some scientific figures we are using in our work. So maybe this picture gives you a sense of fun, and also give you an illustration on what we are working on. Okay, so but before I start to introduce what is cyberpunkian quantum field theory, let me firstly introduce you what is quantum field theory. Okay, so this is a basic concept in theoretical physics and also in modern physics in general. And quantum field theory is basically one of the basic paradigm of almost all subclass of all subjects in the modern research of physics. And here I put some pictures here, and this is a picture for string theory, and this is for black holes, and this is the collider physics, and this is quarks in particle physics. And this is a plot which corresponds to condensed matter physics and strongly correlated system. And this is called atomic physics and quantum information science. Okay, so as we know, and the quantum field theory is basically a paradigm to describe almost all those phenomena. So it's really part of the theory of everything. So you might get confused, and some of you are particle theorists, and you might be particle physicists. You might be familiar that our particle theory currently, the standard model is described in quantum field theory. So we already have many like quantum fields, and in the continuum, we have electromagnetism, and we have scalar fields, and we have gauge fields, in our theory. But how about condensed matter? So since condensed matter is a theory of usually written in the way of quantum many-body physics, which is lattice configuration of quantum mechanics, it seems to be not really a field theory in the continuum. Okay, so answer is that the answer is actually pointed out in the last century, mostly and pioneered by Ken Wilson, who point out the key concept, which is called the Renormalization Group, and which tells us how to define quantum field theory and in a more deeper set, in a much deeper sense. And one explanation is that actually quantum field theory could serve as a low energy limit of quantum many-body systems. Okay, so for instance, if I have a lattice theory and a lattice construction, and maybe your favorite theory about spin chains, and then this could be regarded as a neutral valid theory, and then I could actually when I zoom out, so I keep reduce my energy in the low energy limit, in the long distance limit. My theory will roughly look like a continuum theory, which is this is a basic idea of renormalization group or core screening. So here I'm drawing a renormalization group flow and RG flow here, where the UV theory is your favorite lattice theory, and the IR description in the macroscopic limit is described by a quantum field theory. A typical example of this figure is second order phase transition in your statistical models. If you have a lattice model and quantum lattice model, and you turn to the second order phase transition critical point, and you will find that your theory is described by by a conformal field theory, which is a quantum field theory that is scale invariant, roughly speaking. So then this is a typical example that actually quantum field theory could describe lattice model and condensed matter model, and maybe some models in your cold atomic physics, and as a low energy description. Okay, so here I'm drawing an RG flow, and there are some theories in the middle and between UV and IR. So yeah, so there are very simple quantum field theories, and but they are also very hard quantum field theories. But in general, quantum field theory is a very hard subject. So the simplest quantum field theory is probably the free theory, which is made by a bunch of harmonic oscillators in the continuum limit. Okay, in the free theory, since we all of us already know that how to quantize harmonic oscillators, so we already could solve free quantum field theory, both like bosons and fermions. Okay, and then we could, based on the free theory, we could add the coupling. If the coupling is weak enough, we could actually use the perturbative expansion, and we could do the perturbation theory. This is basically the method of Feynman for his Feynman diagrams, okay? And for the weakly coupled theory, we could actually easily compute the theory, which is not that hard. It does not really require that many memory, that we could directly write down the Feynman diagrams and sum the Feynman diagrams together theoretically. So that is usually the part that could be done already by theory, and theorists already know many answers of weakly coupled quantum field theories. But on the other side, if you turn on the coupling to be high enough, the theory becomes very complicated, and in this kind of situation, we say that it's strongly coupled. In a strongly coupled system, usually it is not very easy to solve, and often we don't have an exact answer in theory, and then it is very challenging sometimes even to define the theory itself. So a typical example of this type of problem is the mass gap problem in QCD in fourth dimension, which is a famous unsolved problem in mathematical physics. Okay, so then there are some known ways to solve strongly coupled quantum field theories, and but still most of them are using some spatial structures in the theory. For instance, if you have conformal symmetry, where the theory is scale invariant, where your theory is integrable, which means that your theory has a large amount of conserved charges, and then you could constrain the theory strongly. And you could also use some ideas like holography, which relates the higher dimensional quantum gravitational theory to a lower dimensional quantum field theory. And you could use the duality and of holography to study quantum field theory using your weakly coupled quantum gravitational theory. And that is also a way to study this, or maybe you could also use some structures in your topology and geometry, or also maybe you could use supersymmetry or some other methods. But all those methods theoretically, and they may not be able to solve strongly coupled theory in general. So in the middle of the RG flow, we have a very general strongly coupled quantum field theory that does not actually have any spatial structures. And in this case, it is very hard to solve the theories theoretically, and there are many unknown problems and need to be understood. Okay, so then a nature idea is that how about just solving them numerically? Okay, so because just now I described quantum field theory could understand as a low energy limit of a lattice model, so maybe I could directly just discretize my quantum field theory and make a quantum many body system, and they have quantum field theory as a low energy limit. And of course, I could start study the theory in this way, and we could, for instance, study the quantum many-body physics by directly by exact diagonalization, for instance, or Monte Carlo simulation. And of course, those numerical methods it might be useful in some case. And actually, this is originally also motivate Ken Wilson to study lattice gate theory. And this is Ken Wilson and taking a picture here. And then actually they have already made lots of progress in this field. And for instance, to predicting some low energy meson mass in a QCD. But as we know, the quantum field theory is a continuum theory, so the qubits you require to solve the problem might be very large. So if you only have a classical computer, and maybe there are many problems that you cannot solve forever. And for instance, there is a problem which is called the real-time dynamics in lattice gate theory. This is a typically hard problem and challenging for the current classical computation. Okay, so this is one of the original motivation for Richard Feynman. And for study quantum computation is because that he wants to using quantum computer to simulate the world. He knows that studying the universe is very challenging and in a classical computer because it requires so large amount of qubits and Hilbert space, and maybe quantum computer could bring us and some solution of those questions. Okay, so then this motivates you to study quantum computation. And the main theme of the talk today I will talk about is to simulate quantum field theories, how to use quantum devices to simulate quantum field theories and compute some interesting observables using quantum algorithms. Okay, but I didn't explain what is cyberpunkian quantum field theory. Let me give a brief explanation. Okay, I'm a big fan of science fiction, and cyberpunk is a typical theme in science fiction. And you might heard of this before. It is pretty well known that if you, for instance, if your cyberpunk stories have robots, and it is usually a cyberpunk story, and usually it's describe a future and where there are many advanced technologies, and there are the information technologies are widely used, and some people can actually becomes robots. For instance, I'm quoting some famous cyberpunk movies and games. There is a Blade Runner, and there is also Ghost in the Shell, and there is a recent famous computer game which is Cyberpunk 2077 that is to appear in this year. Okay, so this is cyberpunk, but what I want to create this term cyberpunkian quantum field theory is that I want to mean that I want to solve quantum field theories, some hard, strongly coupled quantum field theory using some cutting edge cyberpunkian technologies. Okay, so it may not be limited by quantum computation, it might be classical computation as well. The word cyberpunk here, firstly, it is related to the future, and maybe those devices are not completely prepared. For instance, quantum computation, and it is not, we don't, right now, we don't have a very good universal quantum computer that is fault tolerant yet, but it might appear in the future. And also it is cutting edge, and which means that I'm using the most cutting edge and in development, in research methods, in computer science and information technology. And for instance, at least a few classical algorithms, for instance, machine learning, deep learning, and optimization, and matrix product state method, tensor network method, I will talk about later. Okay, so then this is a concept of the term cyberpunkian quantum field theory. So, but here today I will mostly discuss mostly about the quantum methods that is related to quantum algorithms, but I will also briefly talk about some classical methods. Basically, our method is a hybrid quantum classical algorithm. Okay, so then I will start to talk about quantum simulation for quantum field theory. A general introduction is that simulation usually means that I'm using some devices. Maybe it is a digital computer, or maybe it is a cold atomic system. I want to use them to simulate the theory I want to study, and also compute some interesting observables numerically and using my devices. Currently, as pointed out by John Preskill, currently we are in an era of quantum computation, which is called noisy intermediate scale quantum, NISQ, which means that currently we are able to control lots of qubits. Our NISQ devices are already very hard to simulate by classical simulation. However, we are not able to have a universal quantum computer that are efficiently against noise. When we are able to against the noise, we will arrive at the era of full-turn quantum computation, that we will have a very clean qubits with much less error, and we are able to perform quantum error correction. So then currently we are in the next era, and we don't know how long it will last, but we hopefully we will already find there are lots of interesting things to do. Okay, for quantum simulation itself. And maybe you could imagine that you already have a universal quantum computer could perform full Turing quantum computation in a digital platform. And digital platform means that you have a universal gates. You could have all the gates, and you could program your quantum algorithms in a digital way. And you could also try some analog simulation, which means that you could make a cold atomic or condensed matter lab, and you could directly map your Hamiltonian of your quantum field theory or something else to your cold atomic systems, for instance, the Rydberg atoms, and you could actually solve that Hamiltonian or just perform simulation for that Hamiltonian in the cold atomic platform, and you could perform this is called analog quantum computation. You could perform also variational quantum simulation, which is also a hot topic recently. That in the NISQ era, that usually it's relatively hard to perform a universal quantum computation. So sometimes we require some hybrid version that requires a variational optimizer, and then their feedback from quantum devices to solve your problems. So usually this is called a variational quantum simulation, will require some variational algorithm and some optimizations. So those are basic categories of quantum simulation. And today I will mostly talk about quantum algorithms for quantum field theory. So there's a typical challenging task in quantum field theory in the lattice gate theory community, which is to simulate the real-time dynamics for the lattice quantum field theory Hamiltonian. And here I'm describing a method which is called Jordan-Lee Preskill, and which is pointed out by their paper in 2011. Actually, here it is the paradigm for simulating time evolution for quantum field theories. And the typical prototype task is that firstly, there are a few steps. And firstly, in order to start my simulation, I need to encode my quantum field theory basis to the qubit basis. I need to study the encoding. I have to estimate the resource before I'm performing the simulation. Okay. For instance, the simplest method is to use a harmonic oscillator basis. So that for quantum field theory, and then you could encode your system in the harmonic oscillator basis, and then you could study the initial state preparation. And the initial state preparation is the initial state you want to put before the time evolution, and then you have to make that state in your quantum computer. This step could be purely done in the quantum computation way. For instance, you could directly prepare a Gaussian state, which corresponds to a ground state or some excited state for your quantum field theories, and completely using some algorithm in the quantum computer. Or you could use some hybrid way by firstly constructing the quantum field theory states that you're interested in the classical computer, and then use some compilers to compile it to classical system. Both of them are very useful, and specifically the classical compilers and a classical counterpart of the algorithm I will talk about today is the matrix product state algorithm. Okay, and then after you have the initial state, you could try the Hamiltonian evolution. So which means that how to simulate e to the minus IHT in your quantum computer. So this could be done by some standard digital quantum simulation way. For instance, the product formula in the quantum mechanics that I will talk about later. And after time evolution, you could study the measurement problem and how to measure the interesting physical observables you want. And for instance, maybe you want to measure some energy flux, or you want to measure the stress energy, energy momentum tensor, and then you have to construct algorithms to measure them. And usually it could be done by some standard measurement algorithms, for instance, the Hartmart test. Okay, so this paradigm is described in detail in the original paper by Jordan Lee and Preskill. Okay, so it is called Jordan Lee Preskill algorithm. So, okay, then I will describe our work, which is basically, so then the task is that if you have this framework, you could fill each step by your specific input based on your theory. Okay, so our work, I will describe our work, which is working in progress with John Preskill and Burak. And Burak is a previously a postdoc here, and currently he's a researcher in Los Alamos. So then it is a paper in preparation that we are trying to simulate the kink scattering or domain wall scattering problem in 1+1 dimensional lambda phi 4 quantum field theory. Lambda phi 4 quantum field theory is a specific and the simplest quantum field theory you have studied probably in the course. And lambda is the coupling of your interaction, which is phi to the fourth, where phi is a scalar field theory, a scalar field, and we are restricting to 1+1 dimensional because it is simple enough. And then the kink or domain wall in the theory is it could be a highly non-perturbative object. So originally you could actually study the kink solution in a semi-classical limit. For instance, I'm taking some pictures. Actually, those are kinks solutions in two yeah. So these are some plots for the pictures for the kink. Okay, so the kinks are like the object that is that's usually in the theory you have actually two vacuums, two vacua, and the kink is the object is that in the left hand side of your theory you have one vacuum, and in the right hand side you have the other vacuum, and then it is actually the interpolation between different vacua. Okay, so then this is understanding the kink using a semi-classical way, and you can actually find analytic formulas of the kink solution or the domain wall solution, but it is very hard to study when the theory becomes strongly coupled. Okay, in that case, the theory is highly quantum, and you cannot have such a simple description. So the kink scattering problem is also could serve as a standard toy model for cosmic bubbles in electron-wave phase transition. It happens in the early time in the universe, and actually you could imagine that you have two kinks, and then those two kinks collide together, and then the middle of two kinks will shrink, and then it looks like that there is a bubble in the middle that is shrinking. Okay, so this is actually part of this process that happens in the early universe, and it is a very hard problem to study because it might be strongly coupled. Okay, so this motivates us to simulate this process by quantum simulation. So the first we will start at the encoding process. In this process, and you could actually try to encode your quantum field theory basis to your qubits. And of course, if you quantize your theory in the field basis, and the field range will characterize how many qubits you use, because of course the basis, the field is not bounded, and then you have to make some truncation. And actually, the amount of the truncation will determine the amount of qubits, and the amount of truncation is closely related to the field fluctuations. If in your state, the field fluctuates a lot, it is a strong fluctuation, which means that you have to use more and more qubits, okay? And here is an example that we will have some input from the theory and could simplify the answer. And you could actually compute the field fluctuations, actually at least estimate the field fluctuations in the lambda 5 scalar quantum field theory using a property which is super renormalizability in 1+1 dimension, which means that if you do the perturbative calculation in your field theory, their higher loop diagrams are actually convergent. So it is actually only dominated by the one loop diagram. So as a conclusion, in your many states, in your usual states, like the eigenstate of your kinks, or eigenstate of your scalar field, or some vacuum state in the lambda 5 for quantum field theory, and the field fluctuations will almost look like a vacuum fluctuation in the free theory. So this is an example of renormalizability. And then you could use this to estimate the fluctuations, the field fluctuations, and to determine the field range, because we know that in the free theory, the distribution is actually Gaussian. So we could use the Gaussian distribution to estimate the field range, and then estimate the number of encoding. I'm describing this example is because this is a typical example that some physical ingredients are serving as some inputs of your problem. So in order to solve this problem, it is not purely a quantum information problem, but it is also a physics problem that you have to use some physics input to simplify your answer. Okay, for the initial state preparation, we could use some standard method in matrix product state or tensor network to find the answer. So those are done by the classical algorithms, and then we will compile the classical matrix product state to the quantum devices. Actually, here I want to recommend there's actually another talk by Ash Milstead on part of our another work. And then he described in detail how to use matrix product state to simulate the theory. It happens in some earlier IQIM seminar in this year. So if you are confused about matrix product state, you could look at his talk. Okay, so now let's assume that we have the kink description of the matrix product state, and then we could compile them to the quantum devices. The construction of the matrix product state could be done by some standard algorithms. There are some smart people here designing some algorithm which is called DMRG, or rigorous DMRG and rigorous RG, with will control on the error and the system size and some other numbers. We could efficiently estimate the size of your matrices in the matrix product state, or roughly speaking, the bound dimension. And also we could estimate the time cost for preparing the states, and you could find that they are efficient in 1+1 dimensions. We did this calculation in our paper, And this efficiency means that it is almost a polynomial case, which we call quasi-polynomial, that it is, you could roughly regard it as almost it is polynomial in system size, and also the 1 over epsilon. The epsilon is the error you demand. So actually it's an efficient algorithm in the sense of computer science, okay? So after you prepare the static zero momentum kink state, you want to make the kink move. So we have some other algorithms so to do that preparation. But here I want to describe an algorithm that is motivated by cosmology, because we actually have an interpretation that we are simulating cosmic bubbles. So the algorithm is motivated by Coleman's famous forced vacuum decay thought experiment in the last century, that you actually just need to add new potentials to the Hamiltonian to attract the kink. So the new potentials are actually the attractive force you add to the Hamiltonian, and in some approximation, which Coleman called thin wall approximation, and in the semi-classical limit, and he proved that all the energies actually you add to the Hamiltonian are released to the kink. So actually in this case, it is the algorithm is very well controlled, that we could actually turn on this new potential and to accelerate the kink before the scattering experiment. But this may not actually work in strongly coupled case, because this calculation is done in the semi-classical limit, and actually will be a very interesting example of the simulation experiment we could explore if we really have a universal quantum devices to run our algorithm, okay? But we have some other algorithms to accelerate the kink, but this is a particular example that is closely related to physics. And then finishing the initial state preparation, we will arrive at the Hamiltonian evolution, the third task, and which is, here I will simply describe the idea because it is pretty standard. The simplest way to do this digital simulation of e to the minus IHT, and then it's called the product formula, or it's called Lee-Trotter-Suzuki formula in quantum mechanics. And you could roughly regard it as a version of the BCH formula you have learned in quantum mechanics. Actually, the idea is to decompose your Hamiltonian into different terms, and then the whole unitary operation is hard to simulate in your quantum devices. But if you could decompose it to different small terms, and then you could time them together, okay? So then, but this will produce error, and if those Hamiltonians are not commuting with each other. So those errors are well controlled if your time is small enough. So the idea is to just divide your whole time interval to some small, very small sub intervals, and then you could use this algorithm and to do this digital simulation of e to the minus IHT efficiently. Okay, this is a standard algorithm, but there are some other algorithms. And for instance, let me say some name like qubitization, and these are widely used in the current research of quantum simulation of quantum many-body physics, and especially quantum computational chemistry. Okay, and then after this, we will do the measurement. We could measure, for instance, the energy flux or the distribution of some particles in your system, and then we will that's the whole description of our algorithm. Okay, so this is only a formal description of the construction of the algorithm, but actually we could perform some numerical experiment in some simple cases already right now, directly in the classical computer. So here, I will show you an example where, as I described before, an earlier talk is already given by one of the author of our collaboration, Ash Milstead, who is also a postdoc here and currently a scientist in Amazon around Caltech. And then we, in our work, we study some simulation of this King scattering experiment in some toy models. For instance, we are considering some transverse field Ising model in 1+1 dimension plus some extra terms. Those are spin chains, So they are relatively easier to simulate comparing to quantum field theories. So we perform this experiment, and you could say in the plot that in this plot is described the kink profile of the scattering experiments that we originally have kinks. You could say that they will come together and scatter, and they after the scattering, there are some products, and then because of the attractive force, they will be attracted again and bounce again. This is an interesting experiment you could actually perform currently in the classical computer using matrix product state method. And then using this way, we could actually observe some new particles and in our experiment, and using some criterion, and we could also observe the entanglement generation. So this is, for me, this is really cyberpunkian, that this really like simulate and scattering experiments which might happen in some version of your real collider. Okay, but this calculation is done in a classical device. But the problem that of this computation, which could serve as a limitation of classical computation, is that you cannot go to very, very high energy. So for high energy scattering, that we expect that and specifically highly relativistic limit, we expect that there are lots of particles would produce in that process, and there might be a giant amount of entanglement generation, which might be beyond the description capability of your matrix product state. Namely, your bound dimension, your matrix product state will grow very high. So then it is beyond it might be beyond the current capability of classical simulations. So those work and those simulations will be served also as a way to find potential fundamental limitation of classical computation, that even we use the most efficient classical algorithm, potentially we might need quantum computer in the future to simulate the whole process. Okay, so those are basically the description, a very brief description of our work. But later I will talk about some more conceptual concepts about quantum simulation for quantum field theory, which is called the quantum Church-Turing Thesis. Okay, so those Church and Turing are two very famous computer scientists and pioneers in computer science. And the question they have is that, is the world actually computable by your devices? Computable means that you could actually, using your circuit, your digital circuit, to simulate all the physical process that could happen in the world in finite time. So this is called Church-Turing Thesis. A thesis is not really a theorem. It is not proven currently. It is a statement. So it is not a theorem. But it could be proved or it could be disproved, and we don't really know the answer. Of course, the quantum version of the thesis is that, could quantum devices simulate all the process in finite time? Okay, but this is the concern of simulability. Okay, so but a stronger version of the thesis is regarding the complexity of quantum simulation, namely the time cost of quantum simulation. There's a version of Church-Turing thesis which is called complexity theoretic quantum Church-Turing thesis, or quantum extended Church-Turing thesis, QECT, which means that is all the phenomena in the world could be simulated by a quantum circuit efficiently. Efficiency here means the efficiency in complexity theory. If an algorithm could run in polynomial time, we say usually that it is efficient. If it is exponential, then we say that it's computationally hard. It's not that efficient. Okay, so then the QECT, quantum extended Church-Turing thesis, states that the world might be computable and simulated actually efficiently and using quantum circuit. So this is also not really proved, although we don't know any counterexamples. Until now, we don't know any counterexamples about this thesis, but there are indeed some confusion of this thesis. Okay, so these are very much on the frontier of the research that regarding the quantum Church-Turing thesis. the first confusion is pretty simple. That how about relativity? Okay, because we are regarding the efficiency of the thesis. So then, how about just boost the observable and change your time coordinate? Because the complexity is a time cost. If you change the time coordinate, for instance, you change your coordinate from the Minkowskian coordinate to the rendered coordinate in your scalar field, flat space quantum field theory, and the story might be different. Namely, you could boost your observables, and then maybe it will bring your exponentially hard task to some easy task, which is polynomial. Okay, so then this is a confusion, and until now, it is still under research on what is the answer. So it is still in development. So this suggests that maybe we need a version of quantum Church-Turing thesis that is consistent with spatial relativity or with general relativity. Because now we are talking about general relativity, now it is related to gravity. So there are indeed some challenge of the quantum Church-Turing thesis that is discussed recently about holography, which is, as I described before, it is a correspondence between a higher dimensional quantum gravitational theory and lower dimensional quantum field theory living on the boundary of the theory. So an example of this is a black hole. And in the black hole, and we know that the black hole is a bulk object, but its entanglement, its entropy is mostly lying on the horizon of the black hole. And then basically the entropy of the black hole is actually determined by the area. This is an example of holography. Okay, so the ADS-CFT proposal, or the holographic correspondence, that is in some sense an upgraded and more complete, more general version of the holography in black hole. Okay, so actually there are confusions about this because theoretical physicists could derive some formulas regarding holography. If holography is true, they find that entanglement entropy in the boundary theory could directly correspond to the extremal surface area in the bulk theory in the gravity. Okay, so then if that is the confusion, and maybe for some computer scientists, because entanglement entropy is a very hard to object to estimate. Okay, you need exponential resource to estimate a entanglement entropy of a general state. But instead, the area in the bulk seems to be relatively easy to simulate. A similar story happens about the computational complexity. There are proposals that complexity is actually equal to the action, which is also equal to the space-time volume in the bulk. Okay, so then complexity is also a very hard object to estimate, but the space-time volume in the bulk seems to be a purely geometric object that is relatively easy to simulate. So there is actually a confusion between hard and easy regarding holographic correspondence. Maybe you could say that, okay, so actually have, if the correspondence itself, the mapping from the bulk to the boundary, or the boundary to the bulk, is actually exponentially hard. It is a hard process to simulate. Then the dictionary is consistent. Yeah, that is a possible resolution, but if the computationally hard process emerging in the calculation, that means that it seems to be a violation of the quantum extended Church-Turing thesis I described before. So this is an example. Maybe it is a little complicated for non-expert, but this is an example that there are indeed currently widely discussed that there are some challenge about quantum extended Church-Turing thesis and some fundamental research about quantum gravity. Okay, so but what I'm suggesting here is that to study quantum algorithms for simulating quantum field theory is actually a very good way to make these statements more solid and to solve the confusion. Because actually we already know that the quantum field theory is one most important ingredient to almost all theories in the world. So we could construct the algorithms for simulating quantum field theory to find if those algorithms are polynomial or exponential in system size, and if this time cost is efficient or if inefficient. If we could find this and make this rigorous by finding these algorithms, maybe we could get the answer. Okay, simulating, so namely simulating quantum field theory in quantum devices as a cyberpunkian quantum field theory task could be served as a good conceptual question also, other than its practical purpose. Okay, so then there are some other work I have done and with some other collaborators, and some of them are still in progress, some of them are published. And they are about quantum simulation for quantum field theory in some other aspects, this including quantum algorithms for quantum field theory and simulating quantum field theory using some quantum computational chemistry method, and also simulating quantum field theories using hybrid tensor network. And also there are some discussions I have made with my collaborators about Jordan Lee Preskill algorithm in the curved spacetime, especially cosmic inflation. And there are some work I'm working with an IQIM group about simulating matrix models and also using some stringy supersymmetric quantum field theory method like orbifold lattice to simulate lattice gauge theory and EMEA theory. Okay, those are some work that I have done that is related to the general target of simulating quantum field theories. And let me summarize briefly the future direction. So as I point out, I show you a paradigm that is developed by Jordan Lee and Preskill for simulating quantum field theories. And you could, of course, using that paradigm to simulate other quantum field theory you are interested in. You could also simulate curved spacetime ADS-CFT and horography, as I described before. You could also simulate quantum gravity thought experiment. Okay, you could also simulate collider physics and particle physics, strongly coupled QCD and finite temperature quantum field theory, because the simulation I'm describing today is only about zero temperature, but you could actually simulate the finite temperature dynamics that are closely related to some research in nuclear physics. And there are many problems that are not being completely solved there. And then there are also, you could, some directions you could try to do analog or variational quantum simulation, and where you could actually perform some experiment in near-term quantum devices or in your code atomic labs. So there are proposals about quantum gravity, which is related to, also to another IQM similar, other IQM similars about simulating quantum gravity in a lab. And this is also following some similar spirit to my talk here. And also, as I described before, you could try to simulate some conceptual issues about the Church-Turing Thesis. Okay, so those are future directions. And then I guess that's all of my talk today. And then, yeah, so probably I should ask earlier, but does anyone have any questions about my talk?
Thank you. Thank you very much for this nice talk.
Okay, thank you very much. So yeah, so if you have any questions about my talk, you could directly write something up in the asking and answering section, and then I could answer it.
And you also have the option of asking to speak. You prefer you ask the question.
Yes.
So what, like, let's give time to people to think about questions. But I wanted to ask you something. Like you presented some work you've done in like simulating quantum field theories for using like I would say like spin models in a sense, or like many body models.
Yes.
They were all like 1+1 dimensions, right?
So in the yeah, right. So the discussion I'm presenting before it in the whole talk, all those examples are 1+1 dimensions. But in the original Jordan Lee Preskill algorithm, they describe algorithms for higher dimensions. The reason we only consider 1+1 dimension is because we are using the matrix product state to prepare the initial state, because it's the kinks might be strongly coupled objects, so we don't really know. So how to construct those states other than 1+1 dimensions.
All right, thanks.
Okay, you're welcome.
Okay, I don't see any other question coming up. But as I said at the beginning, we are trying with space for having like post-seminar socialization, follow-ups, informal conversations, which is called Gather Town. And so I'm like to invite everybody who has still some time to stick around to join. Oh, we have a last minute question.
We have a question.
It's not in the question and answer.
So you mean we have any questions?
Yeah, it's in the chat box. I can read it for you if you prefer, but it's
I cannot find it.
Okay, so I will read it for you. So Yansu is asking.
I see it. Yeah. You mentioned possible generalization for simulating other quantum field theories. What will be the main challenge for this? Of course, this is related to the physics problem that you are interested in. And in some problems, it might have challenge, and in some problems, it may not be that challenging. Let me give you some examples. For instance, as I described before, if you want to construct kink solutions, in higher dimensional quantum field theory, and to perform a kink scattering experiment, it is relatively hard. Currently, we don't really know, at least in this work, we didn't say anything about how we could do in higher dimensions. So this is a typical example. Another example is that you could, simulating strongly coupled QCD in higher dimension is also very hard. So because of theory, and as I show you, that there are 4 steps, and I think there are many uncertain questions currently and also in development about how to simulating lattice gate series in higher dimensions. And also another challenge comes from the exact implementation, because usually in order to have a reasonable prediction from your lattice version of your quantum field theory to the actual quantum field theory, you actually need lots of qubits. So then it might require lots of resource, and which require you to have a really good quantum devices. And maybe those are some potential challenge for doing this. And also, and there might be some other problems, but those might be related to the actual problem you are studying in physics, like in high energy physics or in many body physics or in like some other areas. Yeah.
All right, I think our time is up. So thanks again, Junyu, for the great talk. And
Great.
If there are like more questions, I
yeah
encourage people to try out.
Yeah.
Our
So yes, my last page on my slide is a cat. So maybe the gesture of cat will amusing you, and also hopefully that you're having a good time and happy Friday. Okay.